In this lecture, we continue the discussion of vector space model. In particular, we are going to talk about the TF transformation. In the previous lecture, we have derived a TF-IDF weighting formula using the vector space model. And we have shown that this model actually works pretty well for these examples as shown on this slide, except for D5, which has received a very high score. Indeed, it has received the highest score among all these documents. But this document is intuitively non-relevant, so this is not desirable. In this lecture, we're going to talk about how we can use TF transformation to solve this problem. Before we discuss the details, let's take a look at the formula for this simple TF-IDF weighting ranking function and see why this document has received such a high score. So this is the formula. And if you look at the formula carefully, then you will see it involves a sum over all the matched query terms. And inside the sum, each matched query term has a particular weight, and this weight is TF-IDF weighting. So it has an IDF component where we see two variables. One is the total number of documents in the collection, and that is M. The other is the document frequency. This is the number of documents that contain this word W. The other variables involved in the formula include the count of the query term, W in the query, and the count of the word in the document. If you look at this document again, now it's not hard to realize that the reason why it has received a high score is because it has a very high count of campaign. So the count of campaign in this document is 4, which is much higher than the other documents and has contributed to the high score of this document. So intuitively, in order to lower the score for this document, we need to somehow restrict the contribution of the matching of this term in the document. And if you think about the matching of terms in the document carefully, you actually would realize we probably shouldn't reward multiple occurrences so generously. And by that I mean the first occurrence of a term says a lot about the matching of this term, because it goes from 0 count to a count of 1, and that increase means a lot. Once we see a word in the document, it's very likely that the document is talking about this word. If we see an extra occurrence on top of the first occurrence, that is to go from 1 to 2, then we also can say that, well, the second occurrence kind of confirmed that it's not an accidental mention of the word. Now we are more sure that this document is talking about this word. But imagine we have seen, let's say, 50 times of the word in the document. Then adding one extra occurrence is not going to tell us more about the evidence, because we are already sure that this document is about this word. So if you're thinking this way, it seems that we should restrict the contribution of a high count of a term. And that is the idea of TF transformation. So this transformation function is going to turn the raw count of a word into a term frequency weight for the word in the document. So here I show in x-axis the raw count, and in y-axis I show the term frequency weight. So in the previous ranking functions, we actually have implicitly used some kind of transformation. So for example, in the 0-1 bit vector representation, we actually used such a transformation function as shown here. Basically, if the count is 0, then it has 0 weight. Otherwise, it would have a weight of 1. It's flat. Now, what about using term count as a TF weight? Well, that's a linear function, right? So it has just exactly the same weight as the count Now we have just seen that this is not desirable. So what we want is something like this. So for example, with a logarithm function, we can have a sublinear transformation that looks like this. And this would control the inference of really high weight because it's going to lower its inference. Yet it will retain the inference of small counts. Or we might want to even bend the curve more by applying logarithm twice. Now people have tried all these methods, and they are indeed working better than the linear form of the transformation. But so far, what works the best seems to be this special transformation called a BM25 transformation. BM stands for best matching. Now in this transformation, you can see there's a parameter k here. And this k controls the upper bound of this function. It's easy to see this function has an upper bound because if you look at the x divided by x plus k, where k is a non-negative number, then the numerator will never be able to exceed the denominator. Right? So it's upper bounded by k plus 1. Now this is also a difference between this transformation function and the logarithm transformation, which doesn't have an upper bound. Now furthermore, one interesting property of this function is that as we vary k, we can actually simulate different transformation functions, including the two extremes that I've shown here. That is the 0-1 bit transformation and the linear transformation. So for example, if we set k to 0, now you can see the function value will be 1. So we precisely recover the 0-1 bit transformation. If you set k to a very large number, on the other hand, it's going to look more like the linear transformation function. Right? So in this sense, this transformation is very flexible. It allows us to control the shape of the transformation. It also has a nice property of the upper bound. And this upper bound is useful to control the inference of a particular term. And so that we can prevent a spammer from just increasing the count of one term to spam all queries that might match this term. In other words, this upper bound might also ensure that all terms will be counted when we aggregate the weights to compute the score. As I said, this transformation function has worked well so far. So to summarize this lecture, the main point is that we need to do sublinear TF transformation. And this is needed to capture the intuition of diminishing return from higher term counts. It's also to avoid dominance by one single term over all others. This BM25 transformation that we talked about is very interesting. It's so far one of the best performing TF transformation formulas. It has an upper bound and it's also robust and effective. Now if we plug in this function into our TF-IDF weighting vector space model, then we would end up having the following ranking function, which has a BM25 TF component. Now this is already very close to a state-of-the-art ranking function called BM25. And we will discuss how we can further improve this formula in the next lecture.